Hey everyone, so I did problem 4 for homework 7 and we're given this graph of inputs and outputs, and we're asked to find the steady state error at different values of R of t, the input. So to do this, we have to actually find the transfer function, and I've laid out how we're going to do that. We're going to use Mason's rule. So once we have the transfer function, we can evaluate this analytically instead of graphically. And these are the different inputs that we're going to use. So first I've made this signal flow diagram, and we're going to find the loops first. So we're going to be using the loops that don't have gains of 1 in them, that have s's in them. So the first one we have is this forward path right here, and then coming back with that minus 4s, and then we have this little loop right there. So here they are with the gains multiplied together, and we've come up with these nice expressions for our loops. Then we define the forward path. So because we have this -1 off the R of s, we're going to start at the next node because they're basically the same node anyway. And that's our first path, and our second path is that 1 and then 2 over s plus 3. So we have some pretty simple algebraic expressions for our forward path. So delta is a little different. We have to follow these summations, but we actually have no non-touching loops, which makes it a lot easier. So it's just going to be 1 minus the summation of those deltas, and it gives us this expression. So for delta sub k, that's also dependent on non-touching loops, and since we have none, it's just going to be 1, which is going to make our calculations for the transfer function much easier. So because delta sub k is 1, we end up with just the summation of our forward loops over delta, and when we break that down algebraically, we come up with this expression for the transfer function. So this is important when we evaluate the steady state error at our given inputs. So for the step function, it's going to be k, or 15, over 1 plus our constant kp. And when you evaluate that limit, because the s terms are bigger on the bottom or higher order, gives us infinity in the denominator, and we get 0. So for our ramp input, it's k over kv, or velocity constant, and we multiply by s, which is going to get rid of that higher order s in the denominator, and is going to be left, once those zeros cancel, with just constants in the denominator after the limit is evaluated. So we have this number 127.5. So the last thing that we have to do is this parabolic input, and because when you take the Laplace of the parabolic input t squared, it actually gives us a 2 in the denominator, so we have to multiply that 15 times 2, let's see over there, to be 30. The acceleration constant is the limit of s equals 0 of s squared g of s. So now the numerator is going to be of larger order than the denominator for that limit, and that's obviously going to give us 0. So 30 over 0 is infinity. There you go.